Welcome back, folks. We're now on week number 4. So the noteworthy thing there is this is going to be the 50% mark. We'll be halfway done with the entire semester on our at the end of Thursday's class. So we're definitely getting there. The next 4 weeks after this one is probably going to move faster than normal, is what it's going to feel like once we're at the end of week number 8. But for where we're at so far with the announcements, we got through our very first exam. Let me scroll up a ways up here. Exam one's official date was week three's Monday. I finally got them all completed, gathered together, and graded on Friday. And so you can check your course grade at any time by just going over here under grades. This essentially updates after every due date goes by, every assignment gets graded, every exam gets graded. And once the full set of exams are graded, you should be able to see your feedback there along with the grade. And you can also double check the full solutions here. I'll post these once everyone's taken the exam. So if I didn't leave enough comments on your exam, you can check that out, or don't hesitate to send me a quick email. I'll be happy to help that way as well. So the other announcement is still on the topic of exams. We have exam 2 coming up next Monday, just so that this second exam doesn't get too overloaded, especially since it was across a major holiday. This one's going to end right on section 3.7, which we completed on Thursday of last class. So it's topics 3.1 through 3.6, pretty much all topics on differentiation, and 3.7 is the applications topic. If you can get through the problems that we solved, the more routine, shorter ones in the lecture notes, through the homework problems in section 3.7, then I'm going to ask a question that's very similar to those, and you'll be in really great shape. But that's the announcement so far. Any last questions or comments at all, folks, before we get started today? Okay, well, as the topic list kind of indicates, we're about to finish off chapter 3 this week. If we stay roughly on target, I'm about a section behind, but that's okay. So our theme for the next topics is more applications to differentiation, exponential growth and decay. Related rates is another section that's kind of infamous, kind of like section 3.5 on implicit differentiation. And in fact, ideas of implicit differentiation get used in that section. So we'll have our opportunity to review how that technique works. We'll be looking into linear approximations, essentially tangent line approximations, and something strange called differentials, which are used later in integration, chapter 5. And then we'll introduce a final class of functions called hyperbolics, show what the derivatives look like, practice around with a few of those, and that concludes our chapter 3. So to start off, exponential growth and decay is kind of a fun section because it's a good amount of review, good amount of algebra review that we'll do in this section. There's still a connection to calculus, so we'll emphasize that each time it comes up. So there's a question also that you might want to take a look into, a warm-up question for the day on implicit differentiation. Getting through finding dy dx on a problem like this one boils down to thinking of y as a function of x, and then look for whenever a product rule, quotient rule, chain rule, anything like that comes up. And that's going to be the key to get through these here. And again, we're going to practice these quite a lot more in section 3.9, really the very first problem. So here's where we're going to start off in section 3.8. We have things that might look familiar. This is the exponential growth or decay formula highlighted down below here. Where it starts, though, however, is the idea of a differential equation. Usually this is not talked about much in a pre-calculus situation, but here we can give bigger context to where this equation came from in the very first place. First, here's the overall context. If we're looking to model a situation with exponential growth or exponential decay, it means the following is true. Y of t is the value of some quantity at time t. If it's a population, we might use p instead of y. If it's a mass, we might use lowercase m instead of y. So we let the context dictate what variable we actually use. So generically here, we'll just use y. Y of t is the value of something, people, money, mass at time t. If that's the case, and here's a critical part, if the change of the amount y with respect to time t is proportional to its size, y at t, at any time t, then we have this formula. Let's break it down, what it's saying step by step. When it says rate of change of y with respect to t, that's just saying dy dt. So that entire part right there is just indicating the derivative. When we say is proportional to, we mean is equal to some constant, which we'll refer to as the proportionality constant, or just a relative growth or relative decay constant. Either way we decide to call it, it's just a constant and it goes here. So if it's proportional to its size, y of t, then y of t also goes here. So we just have the proportionality constant k times y. So it's a differential equation in the sense that there's a derivative on the left-hand side, dy dt. That means to solve this, we need to come up with a function. The solution is not a number like a typical algebraic equation. The solution to this is some function for which, if you differentiate it, you get some constant times the original function in the very first place. So this is what we refer to as a differential equation, anything that has this kind of feature. Just a little bit more context, we'll call this exponential growth equation, or the law of growth, if that constant is positive, or the law of natural decay, or the exponential decay equation, if k is less than 0. It's a differential equation like we mentioned, because the unknown is an entire function. So that's the bigger, wider context that's usually not mentioned very often, at least not with this full notation, in a pre-calculus 1 course. And theorem 2 gives us the full set of solutions to any differential equation like that. Theorem 2 says, if you just write down dy dt equals k times y, it's an equation in the sense that the solution is a function, and this is a bold statement. It says the only solutions to these are these constant multiples of exponential functions. This is the only way you can solve this. You have to have some value, y at 0. Sometimes this is referred to as an initial value, a starting population size, or a starting mass, or a starting amount in a bank account, anything along those lines. It's multiplying by e to the power of k. Here is the proportionality constant, once again, times time. So we claim that those are the solutions, and example 1 is going to ask us to verify that's the fact. Show that it's really going to solve the original differential equation, dy dt equals ky. Well, before we go to solve that, any questions at all with the context or theorem 2? Okay, theorem 2 is pretty massive in a real sense. It's a bigger deal than it seems. We're used to seeing this equation from a growth model or a decay model in pre-calculus 1. But what theorem 2 is saying is, if you set up this equation, the only solutions are these exponential functions. But it goes backwards. What theorem 2 is also saying is, if you take that function y at t and you differentiate it, you just get this, k times y, or k times y at t if you prefer to write it that way. In other words, there is no reason, there is no need to compute y prime, since it is known. In other words, we knew the derivative before we started. The question was, what functions satisfy that derivative equation there? That differential equation is the better way to say it. So if a derivative ever comes up, if we ever have to differentiate that, we don't have to reverse engineer anything. We don't have to reinvent the wheel. We could just use that formula. So that's really powerful as a tool, can save a lot of time. But example 1 is the one and only time we're asked to actually differentiate it and see if it really will solve dy dt equals k times y. So this one and only time, we're going to differentiate that entire equation right there. So let's analyze its form. It involves y of 0 times e to the power k times t. Y at 0 is just a function time. It's the value at the quantity y at time t equals 0. So that means when we see that y at 0, this is constant. We get to use the constant multiple rule then to start off when we differentiate. Next, well, k is a constant in proportionality as well. It's a constant at the same time. So this one is also constant. The variable is there, t. So when we go to differentiate, we just need to observe those constants. We're going to use constant multiple rules twice. And the last thing we're going to need is this requires the chain rule. Chain rules here, it's because it's not just e to the t, it's e to the power of k times t. So that's a modification of just a simple variable t, telling us we do need a chain rule. So with that organization, let's differentiate. In place of y, you can call it y prime at t, just y prime, or I'll go with dy dt just to match the notation. Dy dt is going to be first, through the constant multiple rule, just y at 0. So that value is left untouched because it's multiplying the base e exponential. Next, when we differentiate that through the chain rule, we get e to the power of the inner function times the derivative of the inner function. Let's write in that inner function as k times t. Now, one last derivative to take. But when we go to differentiate here, k times t is like 5 times t or 2 times t. When you take the derivative of 2 times t, you just get 2. K is a constant, just like 2. It's just an unknown constant. But the derivative of this will just be k, because t is to a power 1. So this becomes, let me highlight that again as green. I'm going to take this k and just move it to the far left. Differentiate that. K pops out. Here it is on the far left. We'll be multiplying everything up through here, so y at 0, times e to the power k times t. Forgot to color code that. Let's just hit it with the marker. So here's our whole result. We ran through the chain rule, constant multiple rules. I moved the constant k way out to the front. If we organize this with parentheses, everything that goes inside that parenthesis is the original y at t function. So when we went to differentiate that, the original function just showed up and it's just being multiplied by k. So this becomes altogether k times y at t. But that's what the differential equation is saying here. In a differential equation, we'd often just say y rather than y at t. But we're saying the same thing down here, differentiate dy dt, and we get k times y, or k times y at t if you prefer. So that's really the one and only time we have to use that. We're going to take this derivative for granted when the derivatives come up on the next problem. And we'll know a derivative comes up whenever we see this massive buzzword. Anything that talks about a rate of increase, a rate of decay, rate of change in general, means we're now talking about the derivative. Well, we know theorem 2 is true to a degree. I mean, it has a bigger statement, but that's the only solution. So we'll have to take that part for granted. But any questions or comments at all, folks, with getting through example 1? Okay, well, let's do a couple problems that are pretty typical in an exponential growth decay situation. And then we'll look into some of the new idea that might be new to you, Newton's law of cooling, which is just a small extension from this formula here into some other really interesting problems that involve exponential decay. So here's our kind of a typical generic example to get started with some of these ideas. We are told that bacteria culture grows with a constant relative growth rate. When it says all this, all the information there is telling us that we have a model. We can say, because we're dealing with the population size, population at size t is going to be equal to the initial population, p at 0, times e to the power k times t. So this information implies the differential equation, which gives us that immediate solution. So now that's just a foregone conclusion. It's going to grow according to that exponential growth model. So next they tell us that bacteria count was 600 after 2 hours. So in other words, we can write down an equation. Population size at 6 hours was 600, and I'll just say cells for short on the unit for that one. So we have one function output from there. 8 hours, it's growing exponentially, so it's exploding in size. It comes out to 75,000. So population size at 8 hours is 75,000. That was meant to be a comma between the 5 and the 0 there. So this question is asking us, what is the relative growth rate? Which means this whole question, part A, is solved the moment we get the value for K. Next part is asking what was the initial size of the culture, but initial size, starting population, starting amount, that's always P at 0. And notice the order is actually kind of important here. I can't really get P at 0 first until I know the value for K. Once we know K, we're probably in good shape. So we now have two equations here, these two function values. This becomes a system of equations. We've solved a system of equations in section 3.7, example 2. Here's how that's going to look for this particular one. When this says population size, or excuse me, population at 6 hours in, here's population at any time. We can just plug in for the variable t, 6 hours. So it would be p at 0, e to the power of 6 times k. So all I've done here is swap t for 6. I also put the 6 in front of the k, just looks slightly better that way, equals 600. So that's one equation we get. From over here, the next equation, doing the same kind of thing, plug in the time for t at 8 hours, and that would mean p at 0 is e to the power of 8 times k, which is 75,000. So we used that equation twice, getting these function outputs. Our overall goal is to solve for k, and now with the two equations, we can make that happen. Emma says, why is this p of 6 instead of p at 2? Oh, good question. That was my mistake there. I think the 6 might have thrown me off, but I have no idea where it came from, really. It should be 2 hours. Thanks for spotting that. Might have helped if I highlighted that 2 hours there for my own benefit. So let's put both a 2 here and here. Okay, it was going to be a weird model without that correction there. Other questions or comments at the moment? Okay, again, thanks, that pretty much saves the problem that we would have gotten some pretty weird numbers without that correction. And now that we're in this position, if our goal is to solve for k, notice one thing we can work with. If we can eliminate p at 0 in either one of these equations, we can just isolate for k. So let's solve for maybe p at 0 in the first equation. P at 0 would become 600 divided by e to the power 2k. That can now plug in to this entire spot right here for p at 0. So we make a substitution. Just plug that in right there. And now we have 600 divided by e to the power 2k times e to the power 8k equals 75,000. But now we're in business. We can start simplifying things down. For example, we can divide both sides by 600 in this equation over here. If we do that, let's pull up a calculator on this one. We're taking 75,000 divided by 600. To get an even 125. Exponent loss here would say e power 8k divided by e to the power 2k gives us e to the power of 6k altogether. So now on this equation, this is a good algebra review part on its own. We use properties of logarithms, which there's a couple schools of thought. Convert this to logarithmic form or use a function inverse. Either way, you're going to get the same result. This is the way it's typically visualized. Take the logarithm of the same base as the base exponential. That would be just the natural logarithm. So it's natural logarithm of e to the power 6k equals natural logarithm of 125. Reason we take the natural logarithm is because it's now inverse to the exponential. They undo each other. And now 6k is natural log 125. So that means our work is done. K equals natural log 125 divided by 6. That's a positive quantity, so we have an exponential growth model, and that's the relative growth rate K. So once we got here, even though all the answers to the far right, that's the answer for this problem. Well, any questions at all, folks? Getting kind of half the unknowns in the model settled? Okay, it's kind of a weird dance algebraically when they give us two values, neither of which involved p at 0. If they just gave us p at 0, then part B would be automatic. That'd be a little bit less algebra in this case as well. But once we have k, we also have p at 0 at the same time. We just plug in k right where it appears on the first equation. So we're essentially just now undoing another substitution, and we get that p at 0. This is the initial size of this culture of bacteria, whatever it is. It's 600 divided by e to the power of 2 times k. Let me make that fraction a little bit longer. K, when we substitute that in, is natural log 125 divided by 6. And we need to get a value out of this. Really, there's two ways you can do this. Plug this into a calculator or just simplify it down algebraically. Let's go the algebraic route just to get a little bit more practice on properties of logarithms to see how this goes. If we simplify this by hand, first thing I would want to do is cancel the 2 into that 6. We cannot cancel the base e with a natural logarithm until the coefficient to the natural log is exactly 1. So we do a cancellation. 2 goes into that 6 3 times, so it's really a 1/3 times natural log 125. So after reducing those, we still cannot cancel base c of the natural log until we move that exponent out of its position. But by properties of logarithms, that 1/3 goes right here as an exponent on the 125. So this becomes 600 divided by e to the power natural log 125 to the power 1/3. Now, the next idea is power 1/3 is just a cube root. And the cube root of 125 is 5. But also the important thought is that's a cancellation finally, but only at that step will they cancel. There can only be a coefficient 1 in front of the natural log for the cancellation to be valid. So now it's 600 divided by 125 to the power 1/3 is just 5. And that would go in, I think this is a decent time for a calculator. 600 divided by 5 will give us an even 120 cells. So if the information is accurate, that it was really exactly 600 cells in 2 hours, 75,000 cells in 8 hours, then it had to have started at 120 cells if it's also growing exactly according to that model. That model isn't perfect. It's just going to be fairly accurate in the short run. In the very, very long run, it's going to not be effective at all. The bacteria is going to run out of space, run out of food sources. But if it's following this model pretty closely within, say, 28 to maybe 48 hours, then that's a reasonable expectation. We're expecting 120 cells. Well, if we put everything together, that's all part C is about. The population is size T. We want the expression for the number of bacteria after T hours. That is the expression right where the red dot is, but we had unknowns. We can put in 120 for P at 0, e to the power of K times T. I'm going to rewrite that as T times the natural log 125 over 6. That just seems to fit better on the exponent slot. So that's where the initial size went, and this is where the relative growth rate went as well. So all part C is a big summary. Build out the whole model with all the information we have. Really looks like most of the work was in part A. Any questions to any of these parts so far? Okay, notice we haven't really directly used any calculus at all. And part D isn't even a calculus question. This has all been kind of just algebra review, which is kind of nice. It's a little bit of a breather from last Thursday. When it asks for the number of cells at 3 hours, that's just going to be population size at time 3. So it's just a new function evaluation. One thing we can say for sure is it should be bigger than 600 and probably quite a lot smaller than 75,000. So if our numbers aren't within that range, something is probably off. We're plugging in just a value for T. So this becomes 120 e to the power 3 times natural log 125 over 6. At this stage, we would put this into a calculator, or round to a reasonable number. Let's simplify it a bit just to make the calculator a little bit more manageable. We could rewrite this as 120 e to the power of natural log 125 halves. And you can do more and more properties of exponents on this, just like we did on that step there. You'd have to take the square root of 125. I'd say this is a decent spot where probably a lot of people would put it in the calculator at this stage. So as a calculator value, this is 120 times e to the power of natural log 125 divide by 2. I didn't say what to round this one on, so once again, any reasonable amount, the nearest whole cell or the nearest tenth, maybe a cell division was about to occur as an interpretation there at 3 hours. I'll round this one to the nearest tenth, and you're welcome to use your best judgment as well. So 1341.6 cells. So that's the function evaluation. It's more than doubled from the amount at the 2 hours in. And if it keeps on doubling like that in less than an hour, it's reasonable to expect it to get to 75,000 in 8 hours. Well, the next question is about the growth rate at 3 hours. But here's where we should pause and reflect, because that word is once again a big buzzword in calculus whenever it comes up. When you see rate, growth rate, decay rate, relative rate of change, anything along those lines, we mean derivative. So always try to recognize that whenever you see that. And in this section, it's easy to miss because this is the first time the calculus has come up explicitly. We must use calculus for this part right here. If we want to find the rate of something at 3 hours, we need the derivative of something. And you can differentiate that and then evaluate it at 3 hours. But here's where theorem 2 above in the notes are going to help out. Let's say here, by theorem 2, the rate of change of the population size with respect to time is the relative growth rate K times the size of the population P. So our derivative is done, right? That's spot. All we have to do is evaluated at 3 hours. So this implies rate of change of the size of the population at 3 hours into this experiment would be K times population size 3 hours in. We know the value for K in part A, and from part D, we know the population size at 3 hours as well. So even though this is a calculus step on part E, we have all the information we need. We just need to put them together. This becomes equal to natural log 125/6 times the population size, 1341.6, 3 hours into the experiment. And the unit on this one would be the unit of the numerator, which would be cells, divide by the unit of not exactly a numerator or denominator, but the bottom part, dt, cells per hour. So it's growing at that rate. We just need to plug this in, get a number again. So natural log 125, 6, make sure the 6 is not inside the parentheses on the function notation there, times 1341.6. I'll just use the same thing we rounded to. And so to the nearest tenth, it's growing at a rate of 1,079.6 cells per hour. So that's our conclusion of part E. At the specific time, 3 hours into the experiment, that's the speed of its growth. It's instantaneous rate of change of the population size. At that one and only moment in time, it's growing at that rate. So you might wonder, how in the world does it then get to 75,000? Well, it gets there because if you do this at time is 3.1 hours, 3.2 hours, 4 hours, 5 hours, 6 hours, and so on, that number just keeps on going up and up and up. The population's growth rate is increasing, and that's just how fast it was growing at one specific instance of time. Well, we still have one more question here, still just a little bit along the theme of algebra review. But any questions with this part E, the calculus portion? Okay, well, we knew that population size 2 hours in was 600, 8 hours in it's 75,000. And so if the model continues to be accurate beyond, say, 8 hours, we want to know when will the population reach the size 100,000? So that's a kind of a reasonable question. What we're going to need is the original model. Here it is from the prior part. And now we're solving the equation that goes like this. Population size at time t equals 100,000. All we're going to do is pretty similar to how we started off the part A of the equation. We have the full model for population size at time t, so we just copy it down. On the left-hand side, substitute in 120 e to the power t times natural log 125 over 6 equals 100,000. Then beyond that, we're solving for t this time, but we're going to take the same steps that we did solving for k. Divide out the coefficient 120 into 100,000. I'll call that 83.3 bar. Looks like a repeating decimal. So e to the power t times the natural logarithm 125/6 equals, and I already forgot the number, let me look again, 833.3 bar. Now, at this stage, we can take the natural log of both sides. Natural log e power t times 1 natural log 125, got a division there, divide by 6, equals natural log 833.3 repeating. We did that because of that cancellation there. And now we just get t times natural log 125 over 6 equals natural log 833.3 bar. And by the way, skipping from this step to this step is a very reasonable shortcut. This is just the logic in the middle for the notes to show how it works. But if you feel confident enough with logarithms to go right to this exponential logarithmic form rather, that's a decent shortcut to take. Now last, we are solving for time. The moment we divide by that coefficient there, which means we're multiplying its reciprocal, 6 over natural log 125, into the right-hand side, natural log 833.3 repeating. And we're ready for a calculator answer. Although this is section 3.8, it's not on exam 2. Exam 2 ends on section 3.7. One comment I'll probably make a lot when we're coming up to exam 3 is if you have stuff like this that you're writing down and doing a calculation problem on exam 2, exam 3 more likely, if I see this on paper, I essentially give all of the credit for that. That's telling me you knew how the algebra or the calculus worked exactly. You should still put it in your calculator, get a value out, but make sure you have it on paper, what's about to go into the calculator. That way, even if you make a really simple mistake, I can give you credit right at that step there. I don't want to put a lot of credit on just calculator use itself. So 6 over natural log 125 times natural log 833. Point is 3 repeating, so I guess put in a ridiculous amount of 3's until it stabilizes. But we're rounding this maybe to the nearest tenth once again. This is time in hours. So this would be 8.4 hours if you round it to the nearest tenth. Nearest hundredth would be appropriate as well. It's said that the population reached 75,000 8 hours in. So almost a full half an hour later, it's at 100,000. And that seems to look reasonable for this kind of exponentially growing population size. So 8.4 hours in seems to make about the right sense for this. Any last questions or thoughts at all, folks, getting through this kind of problem? Okay, well, that's kind of the punchline to any kind of growth model that we're looking into. The thing that was new is, once again, anytime a growth rate equation question comes up, we just use theorem 2. It was that dytt equals ky. If the function is p for population, we just put in a variable p instead, but same idea. We don't actually have to take the derivative for this kind of question. We just use the known derivative, so that's kind of neat. It'll come up again on the next question. And for the next question, the next logical problem we should do should be an exponential decay model. However, when we introduce an exponential decay model, it's very, very standard to introduce the concept of half-life. But even for a growth model, a doubling time or tripling time are interesting formulas that you might think about. It just doesn't really come up in the questions that I'm asking in the homework textbook. But half-life can come up. So if we're talking about something growing exponentially, the doubling time, we call it T2, 2 for doubling, is natural log 2 divided by k. Tripling time is natural log 3 divided by k. Seems to have kind of a logic to it, right? And the pattern feels like it breaks. Half-life is negative of natural log 2 divided by k. Just the opposite of that. But to make some sense of this, think about that properties through logarithms. A negative natural log 2 is really a negative 1 times natural log 2. Then negative 1 can be written as an exponent. So this would be natural log 2 to the power of negative 1. And if you want to keep on going, 2 to the power of negative 1 is just 1/2. Natural log 1/2. So the half-life is really natural log 1/2. That seems more logical for half-life, divided by k. So the relative growth rate or the relative decay rate for half-life appears in all of these formulas. And for doing half-life, this is the more standard way to write down the formula. You would get that formula there. But there's really two formulas altogether for every one of these. Sometimes what you're solving for is the half-life, but if the half-life is something that's been already provided to you, and you want to solve for, say, the relative decay rate K, you can just resolve this for K and say K equals negative natural log 2 divided by the half-life lambda. So both equations are equally important. It's usually just stated once in that format there. Well, that's the kind of review of interesting formulas for both growth and decay problems. Half-life being the more important formula. This would be a good one to write down, say, for your exam 3 notes, in case a model like this comes up. More likely than not, I'm going to give you a half-life to go along with it. So we're looking into an interesting radioactive isotope, strontium-90. I believe this, I'm going to have to research that, but I believe this one is used for medical imaging, most likely than not. It has a short half-life of 28 days, which is good if that's the case. It flushes out of your system in a reasonable amount of time. So they provide us a half-life for this isotope. We would typically write down lambda is 28. Part A now begins by saying a sample, we're assuming sample of strontium-90, has a mass of 50 milligrams initially. Well, that's an initial value. It's a quantity at time 0. Because we're talking about mass, I'll use M instead of P, which is for populations. So mass at time 0, the 0th day, is 50 milligrams. Maybe a mouse just arrived at a hospital that does medical imaging. We want to find a formula for the mass remaining after T days. Well, the formula is going to be mass at time T equals initial mass times e to the power K times T. Because half-life is part of the picture, we know we're in the context of something decaying exponentially, which means we get to use the exponential decay model, the law of natural decay, right here. We already have the m at 0 part. All we need is K, and then we can answer this entire question in just really one shot. The K is practically provided. If you know the half-life, you know the decay rate K, and vice versa. If you knew the decay rate K, you would also know the half-life. So unlike example number 2, this one is really fast on part A. So we can just say K equals negative natural log 2 divide by the half-life of 28 days. Let me just highlight that to show where it came from. So here's the color coding on that one. And so the entire answer to this question is mass at time T equals, let's do our 2 substitutions. Initial mass is 50 milligrams. I'll just call it 50, dropping the unit in when we build this function, times e to the power. And it's kind of awkward because K involves a lot of stuff, constants and a negative sign. So I'm going to write it in this way. Negative T times the natural log of 2 divided by 28. So everything in blue here came from K, and I just moved the negative sign in front of T because we can't say T minus the natural log. And inserting more parentheses to force multiplication just makes it look more abstract than it really has to be. I'm going to box out this answer this time because I have kind of algebraic statements floating around everywhere. So when it said find the formula for mass, that's what we needed to end at. Well, we got it. Half-life as a formula is great. We didn't have to work too terribly hard on this one. If we didn't use the half-life formula, we can still get to this stage. Then we'd have to repeat some of the steps that we saw in example 2 part A to solve for K. Any questions at all, folks, getting through that part A here? Okay, well, so far, just like on example 2, we haven't hit the calculus portion yet. And we're still not there in part B. It just wants to know mass remaining after 40 days, which means just do the function evaluation. Mass at 40 will become 50 times e to the power of negative 40 times the natural log 2 over 28. And instead of simplifying it this time, I'm just going to put it all in the calculator in that format. It didn't say what to round to, so a reasonable amount, 1 or 2 decimal places. Use your best judgment would be appropriate. Let's go 50 to the power of negative 40 times natural log 2 divided by 28. So it says we'll have about, I'll go to 2 decimal places, 18.57 milligrams, which might seem about right in a certain sense. If you started off at 50 milligrams, then 28 days later, a half-life occurred, so you're just at 25 milligrams. 12 more days to reach 40 days means you're at less than 25. 18.57 feels about right. It's in the right range for one half-life having occurred and just a little bit more. So that's our function evaluation there. Part C now asks, how long does it take the sample to decay to a mass of 2 milligrams? If this is really in medical imaging, a radioactive tracer in your system, then it's reasonable to ask how long until very little of it remains, just 2 milligrams of the 50. I don't know if they would put 50 of this inside of you, but still it's an interesting question. But the next part, this is a two-part question. What is the rate the sample is decaying at this time? This is where the calculus part comes up, and we need to recall that the derivative is already supplied. dm dt is just k times m, or m at t if you prefer. Even if it's a decay model, the derivative is still exactly the same. So we'll use that formula there once we have the time. So 2 parts to this problem. How long does it take? Let's do the first portion. For the sample to decay to a mass of 2 milligrams. So we want to solve mass at time t equals 2 milligrams. That's solvable for us due to part A because we have the entire model right here. So substitute that on the left-hand side of the equation. We get 50 e to the power negative t natural log 2 divided by 28 equals 2. And we'll solve it just like before. Take 2 divided by 50. I think that's 0.04. We have e to the power negative t natural log 2 over 28 is 0.04. Then take the natural logarithm of both sides. We've seen that a couple times already in the prior example. When you take the natural log of the left-hand side, you just get negative t times natural log 2 over 28. Take the natural log of the right-hand side, 0.04, and essentially we've converted the equation where the red dot is from exponential down to this one, which is now in logarithmic form. And all we have to do is multiply by the reciprocal of negative log 2 over 28 into the right-hand side. Well, both sides, really. So time is negative 28 over natural log 2 times the natural log of 0.04. And throwing that into the calculator will finally give us a value. Let's see what we get here. Negative 28 divided by natural log 2, once I get those parentheses right, times natural log 0.04 comes out as, remember the unit here is in days. I'll round this one to 1 decimal place, 130.0 days. So it'll take approximately that many days for their initial haul of 50 milligrams of strontium to just disintegrate down to 2 milligrams. Well, the rate at its decaying is rapid at first because in the first 28 days, 25 milligrams of it vaporizes. But once we're at 130 degrees, 130 days, the rate at which it's decaying is much smaller because now there's only 2 milligrams remaining at that time. So the question now is, what is the rate? And that's the second part to this problem. Usually if this was an exam question, I think I'd make that part D. But any questions at all, folks, getting through the first part of part C? Okay, now finally for the rate, using this equation, we can say dm dt, the rate of change of mass with respect to time, when t is approximately 130, the unit implied to be days, but I'll drop the unit for the moment, is going to be equal to k times mass at 130 days. The mass at 130 days was implied to be that 2 milligrams. So we don't necessarily have to plug that in. That'd be really close to 2, but we rounded right here, so it'd just be a little bit off. But it's implied that at this time, we're getting exactly the 2 milligrams. So 2 milligrams just goes right inside here, and we already have the value for K that we can plug right over here. So 2 substitutions will tell us that this is equal to first K, negative natural log 2 over 28, times mass at approximately 130 days is 2 milligrams, so times 2. Now back to the calculator on this one. Lots of calculator work today, it seems like. Take negative natural log 2, divide that by 28, double it, and this is at the rate at which it's decaying. It's equal to negative 0.04, negative 0.04. I'll go for 3 significant digits on this one. 0.0495 in units of milligrams per day. So it's a small decay rate because there's not much mass left over 130 days in to this experiment. And also recall where it said decaying is a reason we have a negative sign. It must be negative. A negative in your derivative might mean something is moving down, or maybe to the left in the negative direction, or maybe something is disintegrating, the mass is being reduced over time. A negative always has a directionality, much like a positive derivative means something is going up or increasing in size, or maybe moving to the right in a positive direction, so on. So any word like decay should imply we must get a negative in our answer. And even though it might not feel like a big deal in section 3.8, it becomes a very, very big deal in section 3.9 on related rates. So we'll review these kind of ideas in the next section as well. But that's the conclusion to this one on exponential decay. Any last questions or thoughts on this one? Okay, and as promised, these exponential models are useful in their own right, but if you make a slight tweak to them, you can solve some other very interesting physical situations. And that's the so-called Newton's law of cooling that we'll study for our next 2 examples to close out this section. For most people, this might be a new concept, so let's look into this carefully. It says Newton's law of cooling states the rate of cooling. When we say rate of cooling, we mean a derivative, so that's why we see a dt for temperature over d lowercase t for time. So that's the rate at which something is cooling of an object is proportional to, here's the proportionality constant K, the temperature difference between the object and its surroundings. Here's the difference, and we have a temperature difference between the object at time t and the surrounding. So we're going to let T sub s be the temperature of the surroundings. We'll keep that color coding there. K is going to be decay rate of the model. And this is our differential equation. Now, because it's not a differential equations course, Calculus 2 and a proper differential equations course can show how to solve this, but it's beyond our scope. We'll just take for granted that the only solutions to this differential equation take on this form here. We have the initial temperature, T at 0, minus the surrounding temperature, T at S, times e to the power k times T, plus the surrounding temperature, T at S. So T at S, the surrounding temperature, appears in two locations. T at 0 is just the initial temperature of the object before it was moved from one room to another. That's kind of an interesting model. The problems I have here are kind of standard, nothing too crazy going on, but if you're into like crime documentaries and things like that, these are real models that are used. We can assume that someone has a initial starting body temperature, maybe 98.6 degrees, something like that. And then maybe they were murdered or something awful. And if we take their temperature at, say, 2 hours, or the surrounding temperature, measure the surrounding temperature, we can reverse engineer when the murder or maybe sudden death, something like that, may have occurred. These kind of models are used in lots of a little bit more morbid situations than what we're going to see here. So we're going to look into a couple situations, one where we just use the model directly, another one where we have to use the calculus portion just to get started. Before we begin, any questions at all, folks, with Newton's law of cooling? Okay, well, let's track this one carefully. I feel like I need a different color here. T at 0 deserves a color for this model. It says, just a basic scientific experiment, it sounds like. A thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where the temperature is 5 degrees Celsius. After 1 minute, the thermometer reads 12 degrees Celsius, so it's cooling off pretty rapidly. And we want to know what will the thermometer read in 1 more minute afterwards? We want to know the temperature at 2 minutes, in other words. So that'll be our part A to the question. To do that, we need to use that function there, which means we have to indicate lots of different pieces. That's what makes this challenging. There's 3 big pieces highlighted in those 3 different ways. We can tell what each portion is. We just plug it all back together, and it's no longer so bad. Let's read through this again. Thermometer is taken from a room where the temperature is 120 degrees to the outdoors. What this is implying is the starting temperature at time 0 for this thermometer is 20 degrees Celsius. So we have the initial temperature in Celsius. It's taken to the outdoors where the temperature is 5 degrees Celsius. That's the temperature of the new surroundings. So we can highlight this and say that piece of information tells us T sub S is 5 degrees Celsius. And then finally, one more piece of information is really just a function evaluation. After 1 minute, so temperature at time 1 minute, temperature is at 12 degrees Celsius. So we have 2 pieces we can plug in. We know the initial temperature, we know the temperature of the surroundings. What's missing is K. Once we have the value for K, we can evaluate the temperature at time 2. So let's say we need to find temperature at time 2. The reading of the thermometer after 1 more minute implies that's the whole question to the problem. Put a question mark there. Well, to put this all together, first thing we're going to do is build out the model. We can now say that temperature at time t is the initial temperature, 20 degrees, minus surrounding temperature, 5 degrees, times e to the power, here's our unknown k, we'll solve for that, times T, plus the surrounding temperature again, 5 degrees. So let's simplify this down. We now know that temperature at any time T is 15, e to the power kt, plus 5. Scroll down just a bit there. And finally, once we have that, we can come back up here, use the function value to solve for k. Once we have k, we can evaluate the exact temperature according to this model at any time t. So that's a start. To use this, we identify what all the moving parts are, find them in the context of our problem, then just reassemble them and simplify. Any questions at all, folks, to that stage? Okay, now let's go back up to this piece of information. In this experiment, they made a reading right at exactly 1 minute of 12 degrees Celsius, to the best of their ability to read the Celsius on that. So we're going to assume temperature time 1 is exactly 12 degrees Celsius. But we can take this, plug 1 in for T, and say that this just implies 15 times e to the power of k times, I'll put a 1 there just to imply that's a substitution, plus 5 equals 12. Now back over here, we've solved these equations already quite a bit. Same strategy, let's isolate the exponential. 15 e to the power of k, subtract 5 from both sides is 7. E to the power of k is 7/15. Take the natural logarithm of both sides, canceling out the exponential here. So k is now the natural log of 7/15. And that makes this a modified decaying model because constants can be kind of tricky when you look at that. You should think negative number because the input to the logarithm is less than 1. So you have natural log 7/15. And we really have a decay model, which makes sense. The temperature thermometer is going from 20 degrees, decaying exponentially, getting closer and closer to the ambient temperature of 5 degrees. So we take that K, now we plug it back over here. So the notes kind of crisscross as you go through this process. Plug it back here, and now temperature at any time is 15 to the power of T times natural log of 7/15. Then drop out of the exponent part and go plus 5. So we now can model the temperature using Newton's law of cooling in this way at any time t. And the answer to the question is, what is temperature at time 2? But when you do this kind of thing, it might not be a bad idea, just as a further check on this. If you put in 15 to the power of, oh, I think I forgot something there. It was 15 times the base e exponential. Let me put that in. I think we can squeeze it in just so. There we go. That looks a little bit better. Take 15 times e to the power of, let's plug in 0 times, if I can get a times there, I'll use a parenthesis, natural log 7/15 plus 5. So this would give us 20 degrees. Because I plugged in a 0 for time, that should match up with the initial condition. Now if I plug in 1, if I have the right model, I should be getting 12 degrees. So this is a really good check on our work before we go too much further. Plug in 1, that gives us some confidence, 12 degrees. So now if we plug in 2, that's our answer. 1 minute later, temperature at time 2 is now I'll round to 1 decimal place, 8.3 degrees Celsius. Let's put that in for the notes as well, that the last step is temperature at time 2 15 e to the power 2, natural log 7/15 plus 5, and this comes out as 8.3 degrees Celsius. So that's the resolution to this question here in part A. I want to take a quick screenshot here before we scroll off too far. Any questions whatsoever at all getting through these steps here? Okay, we didn't explicitly use any calculus, but that's a differential equation. So under the hood, calculus was used, telling us that the solution to that differential equation is that particular function there. And for part B, it's still not a calculus question, but calculus will come up in a bigger way on the very next example. Part B is now just asking the question, when will the temperature reach 6 degrees? It's got to be beyond 2 minutes, and it's getting close to the ambient temperature, so it might be a little bit more than we think in terms of temperatures. Temperature drops quite a lot at first, but then as it gets closer and closer to the ambient temperature, it takes more and more time to get these values, and 6 degrees is pretty close to ambient. So I'm expecting quite a bit more than, like, say, 9 minutes, 10 minutes. We'll see what this comes out as. We can rephrase the question as temperature at time t equals 6 degrees Celsius. Then we just come back up to this line. This is temperature at any time. We're just solving an exponential equation again, like we've done on the other examples. Substitution is 15 e to the power t, natural log 7/15 plus 5 is 6. As before, isolate the exponential, so subtract 5 from both sides. 15 e to the power t, natural log 7/15 is 1. Divide both sides by 15. E to the power t, natural log 7/15 is 1/15. Take natural log of both sides. The left-hand side becomes t times natural log 7/15 is natural log 1/15. And I'm running out of horizontal space, so we'll just move to the right. Now multiply by the reciprocal of that coefficient there. T is now equal to 15 over the natural, hang on, let me look at that again. That 7/15 was all in parentheses, so we should be really cautious with that and rewrite it as, let me try it again. T times natural log 7/15. I thought it looked a little bit funny, so sorry for that error right there. Those parentheses are vital with the function notation. When we divide by that, the best way to write it is 1 over natural log 7/15. So that will give us the correct quantity times the natural log of 1/15. So it's just these two logarithms dividing each other. They're both negative, so they're going to come out as a positive quantity for time. And now in the calculator, it's most likely going to look something like this. Natural log of 15 divide by natural log of 7/15 gives us, not as much time as I thought, actually. So we're dropping down to 6 degrees. I thought it was going to be a little bit longer than the 2 minutes. But this one comes out to, say, 3.6 minutes altogether. But we got it, folks. It'll take about 3 minutes, just a little bit longer, for it to drop down to the 6 degrees Celsius on this one. Any last questions or thoughts at all, folks? Getting through the follow-up question, part B. Okay, well, there's still one more question we need to get through to help out with the homework. There's a similar one to both these in the homework set as well. This one, it's the same kind of situation, but when we look at the information provided, it just feels like there's very minimal amount of information to really solve this one. We're told a freshly brewed thermos full of coffee has temperature 98.6 degrees Celsius, so that sounds very scalding, in an 18 degrees Celsius room. When its temperature is 90 degrees Celsius, we somehow know this, it is cooling at a rate of a half a degree Celsius per minute. When does this occur? So once again, we mentioned that these kind of models can be used in crime scenes, and this is the less morbid version of that. So we want to know if it's cooling at that rate, what time did it occur for it to be cooling down at that rate? Let's look through this again. Freshly brewed thermos of coffee has really an initial temperature of 98.6 degrees Celsius. That's the T at 0 part, the initial temperature. So if we're going to use these formulas, we need to translate the word problem into the language of that formula. Temperature at time 0, 98 degrees Celsius. It says this is in a 18 degrees Celsius room. That's the ambient temperature, the surrounding temperature, in other words. So we can now say surrounding temperature, TS, is 18 degrees Celsius. And then finally, it says when its temperature is 90 degrees, it doesn't say when that happens. Like in the last problem, we had a time when the thermometer reached a certain temperature. Here we don't. That's what we're trying to solve for. But what we do know is when its temperature reaches 90 degrees, it's cooling at a rate of a half a degree Celsius per minute. But here's the massive buzzword. When it said rate, it means a derivative. So we have to use that formula there. The arrow looks a little bit awkward. Let me say it this way. Derivative. So we get to use the formula above here, the actual derivative formula, differential equation said otherwise, using this information here. So let's start by saying we're trying to solve for a time, and we can substitute or create a variable. Say t could be that time, or we could call it t naught to emphasize it's a constant. So let's say t naught is the time at which it's cooling at a rate. So we can say dt, d lowercase t at time t equals t naught equals half a degree Celsius per minute. So it's going to be 1/2 degrees Celsius per minute. But this isn't the full story yet, because remember, derivatives have directionality to them. Positive and negative is part of the landscape for these derivatives. And so the trickiest thing here is when it said cooling implies a negative sign. To me, I think that's the easiest thing to miss for a problem like this one. Just like when we said mass was decreasing, the derivative was negative. In this context of Newton's law of cooling, cooling means the derivative is always negative. And if we don't get that negative sign in, it's going to be really hard to track through the problem. So lots going on in this question. It says when the temperature is 90 degrees, it's cooling at a rate of a half degree Celsius per minute. So T naught is the time at which cooling at a rate of a half a degree Celsius per minute, and temperature at time T naught is 90 degrees Celsius. That's the first part of that sentence, when its temperature is 90 degrees Celsius. So we don't know that time. The whole question is, what does T naught equal? So if we can solve for T naught, our work is entirely done on this problem. It's, again, very tricky because there's 3 moving parts in that formula, but they gave us a derivative, which has a directionality sign, cooling implying negative, and another function evaluation. So only 3 sentences, but it's dense in information in all 3 of those sentences there. From this part on, We're ready to get started though. Any questions or comments at the moment? Maybe just do a little highlighting there. Okay, well, we know dt, that's the rate of change of temperature with respect to time, easier to say it that way, is this. So we make a substitution one level down. This whole left-hand side right here becomes K times temperature at time T naught minus the temperature of the surroundings equals that negative, I'll keep that highlighted purple there just to emphasize it, -1/2. So temperature at time T naught is this value, the 90 degrees Celsius. Temperature surrounding, we indicate is 18 degrees. And if we can solve for K, let's see here. Yeah, if we can solve for K, we can get the value for T naught altogether. So that's the setup so far. Any questions at the moment, getting through these stages? Okay, so far all I've done is taken the derivative, use the right hand side of this formula, plugged in time T naught, and so now we can say K times 90 minus 18 is -1/2. Let's maintain that color coding to show where these came from. And so now this is starting to simplify kind of nicely. This just means 72K is -1/2. If we divide by 72, let me go to the right, I'm running out of space again. We get that K equals -1/144. So that's our decay rate K. Now that we have the value for K right here, we have an initial value, 98 degrees Celsius. We can now plug together this entire model. We couldn't do that at the very first step because the decay rate, K itself, was unknown. But using the information about the derivative here supplied at time T naught, it allows us to solve for K. So now in the next step, we can say, therefore, temperature at time T, any time T, is now, take the initial temperature, 98 degrees, minus the surrounding temperature, 18 degrees, times e to the power of K times T, plus the surrounding temperature, 18 degrees. So we have a computation and another substitution to get through. Temperature at time T is therefore equal to 80 e to the power of T, let me write it this way, -T, divided by 144. So the blue part here is the value for K, the relative decay rate. I just put T up in front so we didn't need excessive parentheses to indicate multiplication, plus AT. So we're done with the formulas above, but we still haven't answered the original question. When its temperature is 90 degrees Celsius, it's cooling at a rate of 0.5 degree Celsius per minute. We want to solve what does T naught equal, but that means we can just go to this line, temperature at time T naught is 90 degrees Celsius. So going back to that equation there in that color, whatever color that is highlighted here, we can now solve this equation for T naught because over here we have the temperature at any time. We go take this entire output, and this left-hand side, all we're doing is plugging in T naught for that variable T, right where the red dot is, if it would hold still. So the left-hand side becomes 80 e to the power of negative T naught divided by 144 equals, or don't forget the plus 18, that's gonna make a big impact. Plus 18 equals 90. Now we're about to resolve the whole question. The moment we solve this equation here, for T naught. Well, this one's a journey for sure. Any questions at all, folks, getting to this stage? Okay, let me see if we can get through the next part without having to scroll too much or zoom out too much. It's good to see the whole question if possible. But really, at this point, we're kind of coasting. We're isolating the base e exponential. So it's 80 e to the power of negative t naught. For 144, we're subtracting 18 for both sides, so we get 72. So 80 divided by 72 sounds like kind of a nice round number. It is 0.9 exactly. E to the power of negative t naught over 144 is 0.9. And we have to scroll. Let's scroll down a bit. Take the natural log of both sides, and you'll get negative t naught over 144 equals natural log of 0.9. And then finally, t naught is negative 144 times natural log of 0.9. So here we multiply by the reciprocal of negative 1 over 144. So negative 144 times the natural log, 0.9. Looks concerning, but it's in fact a positive number. This would be at 15. Let's round it to 0.2. 15.2 minutes. So let's take a full view of this. It's in a thermos, so it's not losing temperature very fast. Starting off at a scalding 98 degrees Celsius. Ambient temperature is cool at 18 degrees. And all we knew is someone made a measurement, but they didn't tell us what time it happened. They found at 90 degrees, it was losing temperature at a rate of a half a degree Celsius per minute. We found that the temperature at 90 degrees occurs at T naught 15.2 minutes after it was put into that 18 degree Celsius room. So it took about 15 minutes, a little bit more, to drop 8 degrees Celsius, is what this is saying altogether. Well, we did it, folks. I think this is one of the more challenging problems. Probably not a great question for an exam 3 setting. I would say everything but this one would be a good one. But this is a great one to really delve into these formulas more closely. In particular, see how the calculus portion can enter into problems in many more practical situations. And there's a problem similar to this one in the homework as well. So if you feel stuck or lost on the homework, take a look at this one for the guide, but don't hesitate to ask about it. Well, with our remaining time, we're going to take a look into the very next section, where we're going to be reviewing implicit differentiation with the concept of related rates. But any questions or thoughts before we take a look into that next section? Okay, let's take a look into it. When we come back on Wednesday, we'll be getting through section 3.9 and 3.10 likely. But here's our initial look at related rates. Related rates are tricky because of the way the differentiation goes for these kind of problems. Oftentimes, we're doing implicit differentiations because whenever you see a variable, say x and y, they're both functions of a different variable. We open up implicit differentiation for just a moment. That's pretty much the nature of what's going on. Say on this part to D, where we did the same problem 2 different ways, when we went to differentiate this curve, we had a y squared here, which meant y was truly a function of x itself. So whenever you go to differentiate y squared, you're using the chain rule in this kind of format. You get 2 times y prime altogether, which just becomes a 2y times dy dx. Same thing we saw right here. But we're expanding on this because here x was just an ordinary variable. It wasn't a function of some other variable. So that's where we're going to expand even further than implicit differentiation, but the themes are very, very similar. It says here, x and y are both functions of time measured in seconds, and distances are measured in meters. So here's the whole context of this one. It just says a particle. So this could be some weird proton we're tracking in space, maybe in the Large Hadron Collider, where they do high energy experiments and things. We're going to say that this particle, whatever it is, it's moving along this curve. So this is its trajectory. X and Y are functions of time, which might mean -2 is -2 seconds. That's kind of awkward, but we're going to be focusing on the right branch. The particle is moving across this trajectory here. So if X and Y are both functions of time, that means X is some function, f at t, Y is some other function, g at t. These are unknown functions. But when we go to differentiate, we have to use the fact that when you see x squared, that's a chain rule. There's two functions there, x, which is a function of t, and the squaring function. When you see y cubed, same story, there's two functions there. And x squared times y cubed, that's really the product rule first before we even get to the chain rule. So we'll look at those steps carefully when we go to differentiate this equation. But before we even start to differentiate, we're going to revisit the theme that we saw in just the last section notes, that when we take derivatives, they're indicating directionality as well. Positive derivative means moving in a positive direction, whether that's moving up or down, left or right, growing or increasing in temperature, and so on. Here we're told dy dt is 1/2 meters per second. X is 2 meters. And if that's the case, if the particle has those two features going on for it, that's the rate of change for the y coordinate, and that's the position of the x coordinate. We just want to know which horizontal direction is the particle moving. Is it going to the left or is it going to the right, given this information? So here's how we deconstruct this. Not a bad idea to start with the position. X is measured in meters for distances. Time is measured in seconds. So when we say X is 2 meters in, here are the coordinates. We are right here on that spot on the curve. So that's where X is. When it's asking which horizontal direction, we want to know, is it moving to the right or is it moving to the left? And we have the right amount of information to resolve that. If we're told that dy dt is 1/2 meters per second, we can then conclude dy dt greater than 0 means the particle, according to the y direction alone, is moving upwards. So if the y coordinate has a positive derivative, it means it's not losing altitude, it's going up. So now back to the map, its trajectory. If it's going up, if it's moving upwards, that means overall, it's got to be moving to the left on this. And that's the only way you could stay on this trajectory. If it was right here at 2 meters, but it was moving down, that means it's sliding down this trajectory, means it's horizontally moving to the right. So if it's has a positive derivative, dy dt greater than 0, that means it's going this way. Dx dt is less than 0. It's moving to the left. So that means it would have a negative derivative altogether. So we can come down here, positive derivative means the particle moves upwards, which then implies the particle is moving to the left. So part A is kind of a fast problem. We didn't actually have to do a derivative right here. We just had to have an interpretation of what the derivative is conveying in the very first place. Well, any questions at all, folks, getting through part A? Okay, well, in part A, we know it's moving to the left and the derivative is negative. But part B is now asking, what is the rate at which the x-coordinate of the position particle is changing when the rate of change of the y variable is a half, like in the last part? The wrong color there. There we go. And x is right here at exactly 2, just like on the last part there. So here's where we do need a derivative. So we go back to the start right here. We have two functions. We have the x variable with the y variable. They're functions of time, independent functions, so different letters. So if we're going to differentiate this equation, we require the product rule. So let's maybe copy it down so it's just available here for us to eyeball. X squared times y cubed equals 4 over 27. We start by just differentiating that whole equation there. Product rule says you have to differentiate the variable with respect to x first. So when you do that, this is also the chain rule. The power 2 comes down. The new power is 1. Then we multiply by the derivative of whatever is on the inside. The thing on the inside, the inner function, is x. So x goes here. And multiplying by the derivative, we could call it x prime. Well, let's keep it in Leibniz to match the rest of the notation of the problem. It's times dx dt. Then we just copy y cubed. So we took the derivative of the first thing. Here's 2x. Because the chain rule is part of this, x is a function of time. As per the initial part of the context, there's a dx dt. Copy the y cubed. Then do it all over again. There's a plus in the product rule. We copy the x squared, so it copies down. Next, we differentiate the variable with respect to y. But it's a chain rule again. There's an inner function, power 3. Excuse me, an outer function, power 3. The inner function is y. We differentiate the power 3 function first. It becomes 3 to the power of something times 2. Then we multiply by the derivative of that something. That something is the inner function, so it goes here. That's just a 3y squared times the derivative of y with respect to time, so dy dt. So that's the derivative of the entire left-hand side. The right-hand side is just 0, since it's the derivative of a constant. That's kind of nice in a way. So we want to know what is the rate of change of the x-coordinate of the position particle changing, the rate at which it's changing when dy dt is a half and x equals 2. That means we're just trying to solve for dx dt. And we can definitely do that in this equation. We have just about all the information we need. Let's maybe start by simplifying the equation a little bit more. This would read as 2x y cubed dx dt plus 3x squared y squared dy dt equals 0. We're going to need a value for dy dt, but we have that. We're going to plug in 1/2. That's how fast the altitude of the particle is changing, the y coordinate. We're going to need a value for y and a value for x, but we do have a value for x itself. We can plug in that x value here and here. So all that's missing is a value for y, and then we can solve for dx dt. That'll be the rate of change of the x coordinate of that particle. So the value for y is missing, but we can get it pretty fast. This is the fundamental relationship between both coordinates of this particle, its trajectory. So if x is 2, we can just say 2 squared times y cubed is 4/27. Plug in the value for x there, and now this just becomes a fast equation to solve. 4y cubed is 1/27. So y cubed, excuse me, 4/27. I don't know how that turned into a 1. Divide both sides by 4, and we get 1/27. take the cube root of both sides, and we get y equals 1/3. So now we have a value for y. We can plug in, let's go with this color again. 1/3 will go both here and here. So now it's just kind of a big messy equation from which we can solve for dx dt. Substituting that all in, we have 2 times 2 times 1/3 cubed plus 3 times 2 squared times 1/3 squared times 1/2 equals 0. So the 1/2 came from dy dt. The 1/3 is the variable y. And the 2's you see here are the variable x, and I missed something. I forgot to carry down dx dt. All right, let's just squeeze it in right there. Sorry for that miscopy. Now we can finally solve for dx dt. It just becomes a quick equation at this stage. This is 4/27 dx dt plus, this is going to be 12/9 times 1/2 equals 0. Notice we're getting kind of shy on time, so let me see if I can get through this without going over. I have a 6 there. So 4/27 dx dt is, that reduces to 2/3, so it becomes -2/3. Let's move to the right. So dx dt multiplied by the reciprocal of the 4/27 will give us 27/4 times -2/3. And more reductions to go on this. This is one of those problems that just keeps on going. I'll get a 9 going that way and a 2 going that way, which implies dx dt is -9/2 meters per second. So that's the rate at which the x-coordinate is changing. It's negative, which guarantees it's got to be moving towards the left. That's what part A was all about. It's kind of just a bit of a mental check on where's the particle, what direction is it going, if dy dt is positive in the very first place. So we knew on the onset it had to be negative, and now we know specifically it's moving to the left at the rate, -4.5 meters per second. Moving really fast, because if the rate of change for that variable is 1/2, going 1/2 meter per second means that's a big jump. You have to move to the left quite a bit to stay on this trajectory in the original curve. Well, this is really the major punchline with what goes on with related rates. We're going to look at other scenarios, one with something common in physics, Boyle's law, something more about geometry, people moving around a starting position, and something really practical, mechanical engineering. How fast is a rod on a crankshaft moving for this basic engine here? All these are related rates where there's more than one function dictating multiple variables all at the same time. So this is a theme that we're going to see in more and more questions as we solve this on our next lecture. But this looks like a good stopping point for us today. We're not going to attempt another one in just 1 minute's time. I think that's a bad idea. But any last thoughts or questions at all, folks, before we call it a night? Okay, well, have a great night, everyone. We'll review how we're doing these derivatives going from this line to this line very carefully in the very next problems. It's kind of a redo of implicit differentiation, probably one of the trickier techniques that we've been studying so far. And so if you have any questions, don't hesitate to reach out. I'll be happy to help. But I'll see you all on Wednesday's class, where we'll just continue to the next example.